Hey guys, my name is Tensor. Today I'm going to be taking you through a set of libraries that I wrote on behalf of the IOTA organization. When I wrote these libraries, the name that I wrote them under was called Party. The name has now become tentative and subject to change. It's very possible that when you watch this video, the name will be something different. These libraries are basically just the low-level libraries for a larger project called Stronghold. And the main purpose of these libraries are to create a protocol for storing and securing certain types of data. One of the use cases for this library, for example, is for a crypto wallet. And so with a crypto wallet, you've got a key pair, you've got a public and a private key, and you want to keep that private key as secret as possible. So you need to store it somewhere in memory and maybe somewhere on the disk, but you need to encrypt it and you need it to be inaccessible by anybody but the person who owns the key. Another major focus of this library was to create something that was extremely extensible. So you'll see as we look over the code that there are a lot of traits, and Rust traits are essentially just interfaces. And you can just implement these interfaces to use the logic in these libraries. All right, so the first library that I wrote was this primitives crate. And the primitives crate is just a bunch of cryptographic primitives described as traits. Here we've got a trait called cipher, and a cipher, of course, is an algorithm that allows us to encrypt and decrypt some data. The trait itself just describes different functions that need to be implemented to create a cipher inside of the Stronghold protocol. We've also got traits for random number generation. We've got traits for signing. We've got traits for message authentication. We have traits for hashing, and we have traits for key derivation functions. Along with all of the traits that are in this crate, there are a bunch of info structs, and each of the types has a specific info struct associated with it. And these info structs describe metadata about the trait that you're implementing. So if I wanted to implement, say, a cipher, I would implement the cipher and I would implement all of these functions. And then to tell the system more about the cipher, I could then create an instance of this struct. So I'd put in things like the ID of the cipher, then I'd put in whether or not the cipher is a one-time use cipher or not. Then I could put in a range of the supported key lengths, a range of the supported nonce lengths, and a range of the supported authenticated encryption with associated data tag lengths. And so you can see how this metadata would be useful for the system and for people who are using the system. Now directly on top of this primitives crate are two other crates. We have a Cryptocrate and a random crate. The random crate implements a random number generator, and so you can see here that it actually pulls from the primitives crate a trait called secure RNG, and then we implement that secure RNG trait for this OS RNG struct. And the way that I set up the random number generation for this library was by using a bit of C code. All of the major operating systems have battle-tested C libraries that provide random number generation, and so it makes sense to leverage these libraries. For example, on Windows, we can include the windows.h header and the WinCrypt header, and then we've got a bit of Windows-specific logic that we call to fill the provided buffer with random bytes. The C code is glued to the Rust code through this build.rs file, and we use a library called CC, which leverages the C compiler, and what it does is it just uses a set of instructions to compile the C code into a library, and then we can use cargo to link that library to the Rust code. And if we go back into our Rust code, you can see the FFI. So we have the external function, the external C function here, called osRandom secRandom. And we're calling this inside of this random method, and we're using it to fill the buffer that we supply with random bytes. Now let's look at the Cryptocrate. The Cryptocrate implements 5 different cryptographic algorithms. And these 5 different algorithms are actually based off of 2 main algorithms. So we've got ChaCha20 and we've got Poly 1305. And these are the 2 base algorithms that we use to derive the other 3 algorithms. And the other 3 algorithms include XChaCha20, ChaCha-Poly, and XChaCha-Poly. Now, all of these algorithms are implemented internally with macros. And one of the reasons I did this was to make the algorithms as composable as possible. If we look at these macros, we've got some fairly basic functionality here. For example, we have a add function, which uses a wrapping add, which is a modulus addition. Then we've got modulus subtraction. We've also got modulus multiplication. We've got modulus bit shift right and bit shift left. Then we've got modulus negation. And we've got a bunch of logical or Boolean operations, such as OR, AND, XOR, greater than, and equal. Now, if we take a look at the internal functions for our encryption algorithms, you can see that we're using these macros together to derive the method of encryption. So in the case of ChaCha20, we use a bunch of AND, XOR, OR, shift left, shift rights, and so on. Also, each of our encryption algorithms implements from the primitive trait. For example, XChaCha-Poly implements the secret key gen trait from our primitives crate, and it also implements the cipher trait from the primitives crate. With the Cryptocrate, one of the important things was to verify that the algorithms were completely consistent. And so I wrote a fuzz client to do this. And what a fuzz client does is it takes the algorithm and it allows you to insert random inputs and verify the outputs. And so what I did to achieve this was take the sodium oxide library, which is based off of libsodium, and take its version of ChaCha-Poly and XChaCha-Poly, and then compare those with our version of ChaCha-Poly and XChaCha-Poly. And because ChaCha-Poly and XChaCha-Poly are derived from Poly and ChaCha and XChaCha, they also prove that the other algorithms are consistent. I was able to run this fuzzer client up to 10 billion inputs, and it was completely consistent all the way through. Now let's get into the main meat and potatoes of our library. On top of the primitives crate, the random crate, and the Cryptocrate, we have this vault crate. And the vault crate is a in-memory database specification which allows us to define versioned data and how that versioned data will work. It's important to note that this data layer doesn't actually define the data structure that stores any of this data in memory. Instead, it just defines how the data will be stored in memory. So you could use something like a hash map, or you could use a more complex data structure to store the data, and the library doesn't really care what you use. Now, the way this works is that each piece of data has its own data chain or data graph. And the data chain starts with an initial transaction or init transaction. The init transaction itself doesn't actually have any data inside of it, but the system creates it as the main node of the graph or the beginning of the chain. Then after the init transaction is created, we can now start to add data transactions to our chain. And the data transactions, at least all of the valid data transactions, will be direct descendants of the init transaction. We have a data transaction here, or a data record here, and it's a direct descendant of the init transaction. And then we also have another data record here, which again is a direct descendant. And then we've got this invalid record here, because it's a descendant of this data record rather than the init transaction. And the way that we know which data record is the latest version of our data is by reading a counter that is used internally inside of all of these transactions. So when we create our first init transaction, the counter is 0, then we add a piece of data, the counter goes up to 1, then say we add another piece of data, it goes up to 2, and so on. We also have the ability to revoke records from our chain. So say we want to remove one of our data records, we could create a revoke record with a reference to that data record, and then we could call a function called garbage collect, which would go through the chain and remove the data record and the revoke record. The main data structure for this vault crate is this dbview data structure. And the dbview data structure contains a key, which is the secret key that we use to access any of our data. Then we have a chain record, which is the chain of all of our records. And then we have a valid record, which is a chain of all of the valid records. That is, all of the records that are direct descendants of the init transaction that are associated with this DB view. The database view itself is just a view over a data structure. And if we want to, say, read the data, then we need to convert the DB view into a DB reader. And if we want to write to our data structure, then we want to convert the DB view into a DB writer. And of course, we have associated methods to do each. The DB view implements box provider. The box provider is how we encrypt our data. So we've got a trait here called box provider, and it's got a bunch of methods associated with it. And then we've got our key down here, and the key also has the box provider inside of it. And if we go down to the bottom here, we have two main traits, one for encryption. So this uses the box provider to call to box seal, which is one of our encryption functions. And then we take that sealed data and we pass it back. And then we have decrypt, which uses the box provider to open the box. The Vault library also has its own fuzzing client. And the idea here is to take a bunch of random data and then pass it into the database using a bunch of random transactions. If we look down here, we have a worker, and the worker uses a random number generator to decide what it will do with the data. So we could either create a record, revoke a record, or perform a garbage collection. And based on what happens, various different things will be printed to the console or to the standard out. Every time the fuzz client does one of these actions to the database, it sends the action into this connection interface, and the connection interface sort of simulates a network connection. The idea here is that we've got two hash maps, and our two hash maps are basically two vaults, and we compare the two vaults to verify that the data is consistent across both of the vaults. The fuzzer also will do a certain number of transactions based on a number that's specified by an environment variable by the user. So if we wanted to verify the databases after only, say, 10 transactions, then we would specify this number. Or if we wanted to have, say, 1,000 transactions before we verify the databases, we could increase this number. We also have a machine struct, and the main purpose of the machine is to assimilate a random chain every so often. So after validation, after we validate that our chains are all valid, we have the machine go ahead and take ownership of one of the chains in our vault. And then we run a series of transactions again, and then we re-verify that the transactions are all valid. Alright, so now let's look at the snapshot crate of this library. And the snapshot crate is essentially the file persistence layer. With the vault, we have all the data sitting in memory, and if the application ends or quits, then we need to offload that data into some kind of file format. And so that file format is specified by this snapshot crate. One of the main purposes of the snapshot crate is to make it so that after you've offloaded the data into a snapshot, you could take that snapshot, put it into any Stronghold system, and reboot all of the state back into that system. So you could literally take a system, create a snapshot from it, and then copy that state into a new Stronghold system. Alright, so of course this document needs to be encrypted, and it's encrypted using a password encryption algorithm, and we're actually using Cha-Cha Poly from libsodium to do this. So the document format is as follows. We have a signature, and we take the bytes of the signature and we just feed it into the top of the file. Then we have some version bytes, and we feed those into the top of the file. And the version bytes just verify that the user is using the right version of the program. If the snapshot algorithm changes in some way, then we want to change the version, so it will then invalidate all of the older snapshot variants, and then we can have those snapshot variants be updated to the latest version after they've been verified. Then after the version bytes, we have a hashed salt, and then we have our header bytes, and then finally we have the encrypted state data. So basically, to create a snapshot, we need the state data, which we get as a buffer, and we need the output file that we want to output to, and then we need a password from the user. We generate a salt using libsodium, and then we use the password and that salt to derive a key. Then we take that key and we use it to create a stream and a header. And of course we're writing all this stuff into our file. So we have the signature, the version, then we have the salt in the file, and then we go ahead and we write the header to the file. Then we take all of this state data and we read it through the stream, and the stream encrypts the state data, and then we push that data into the file. Then to decrypt the snapshot, we just kind of reverse this process. We go ahead, we read the header, then we read in the salt, and of course we need the password from the user. We use the salt and the password to rederive another key. Then we go ahead and we use the key and the header from the file to create a pull stream, and then we pass the data through the pull stream, and that decrypts the data. The most important thing to note about all of this is that the snapshot protocol can encrypt any data so long as the data is in binary format. So long as our data is represented as bytes, we can encrypt it and decrypt it with this snapshot format. And that's how we're able to take the state of an entire stronghold and put it into a file. I also created an example command line interface for this project, and of course this uses all of the libraries that we just talked about. Each of the libraries also has a set of testing functions, and as we mentioned, the crypto and the vault library have their own fuzz clients as well. But this is mainly just to show off the functionality of this set of libraries. Alright, so let's go ahead and take some data and put it into our vault. And because of the way that the CLI works, what this will do is it'll take the data, put it into the vault, and then immediately offload it into a snapshot. So we need to pass in the data that we want to encrypt, and I'm just going to pass in a string of some data, and then we need to pass in the password for the snapshot, which in this case will just be password. Now we can go ahead and list the IDs for all of the records that are in our vault. And of course, to do this, we'll need to read from the snapshot, so we'll need the password. And as you can see here, we get back the ID of the transaction and the hint of the transaction. And we can use this ID along with the password to decrypt the snapshot, put it into the vault, and then read the data back as plain text. And as you can see, we get back the plain text some data. Now let's say I want to revoke the data that we put into our vault. I can go ahead and put in the ID of the data and the password for the snapshot. And now when I go to list the data, you can see that it doesn't list anything because the data now has a paired up revoke transaction. And if I want to delete the data from the vault completely, I can run a garbage collection. And the garbage collection will go through, find all of the revoke and the associated data transactions, and then delete those. So again, if we call list, we get nothing back because all of the data has now been removed from our snapshot and from our vault. And that's really it. So the CLI is as basic as it comes. It's mainly just used to show off how you can do these things, how you can do the basic things with the protocol, and show off a way to create a data storage with the Stronghold libraries. Alright guys, well I hope you enjoyed this video and I hope you found it informative. I know it wasn't as in-depth as most of my videos usually are, but that's because this project is so large. If you want to find out more information about the project, or if you want to look at the code, it will be public by the time I release this video, and you can go ahead and take a look at the GitHub repository, which I'll post down below, and you can take a look at some of the other things that IOTA is doing with this library over the next few months. Have a good night.